To keep the modern world running, we need a constant, massive flow of energy. But the easy, accessible reserves are largely gone. Today, the most valuable untapped deposits are buried thousands of meters below the ocean floor, in some of the most unforgiving environments on the planet. Extracting those resources means building isolated industrial outposts far offshore. These deepwater platforms and FPSO vessels are designed to withstand constant bombardment, engineered to hold their position through Category 5 hurricanes and towering 30-meter waves. To understand the sheer vertical scale, you can stack the entire Statue of Liberty next to one, and it barely reaches the main deck. This financial counter reveals the staggering barrier to entry. Before a single drop of oil is pumped, designing, building, and deploying one of these deepwater units can easily require an upfront capital investment of $10 billion. Despite the massive costs and the extreme environmental hazards, these floating cities are an absolute necessity. Right now, they operate as the only viable bridge connecting deep Earth energy to the civilization that relies on it above. The physical journey begins far below the hull. A heavy drill bit is sent thousands of meters beneath the seabed, violently grinding its way down through thick layers of solid rock. To drive that bit deeper, the towering derrick on the platform continuously rotates a miles-long steel pipe known as the drill string. At the same time, it pumps down a steady stream of a highly engineered chemical mixture called drilling mud. This mud serves a dual purpose. It cools and lubricates the grinding metal, but more importantly, it provides shear weight. The heavy hydrostatic pressure of the mud column pushes down, fighting back against the massive natural pressure of the reservoir waiting below. If that balance is lost, the consequences are disastrous. When the reservoir's pressure violently overpowers the weight of the drilling mud, it triggers a blowout, rocketing volatile fluids up the pipe and causing massive, uncontrolled fires at the surface. To prevent this, the industry relies on a massive subsea failsafe called the blowout preventer. Sitting directly on the ocean floor, it contains mechanical rams that instantly slam shut, physically crushing the pipe to seal the well if pressure spikes. Reaching the oil is only the first battle. Safely capturing it and bringing it up to the platform requires a flawless, continuous balancing act of extreme geological forces. Even when the fluid safely reaches the surface, it is far from pure, market-ready crude. What blasts up the pipe is a chaotic, high-pressure, scalding mixture of oil, highly volatile natural gas, salt water, and sand. This raw mixture arrives at the platform's topside processing module. It is a dense, highly complex labyrinth of high-pressure lines and control valves designed to sort the raw materials. This diagram shows the core component in this maze, the horizontal three-phase separator. This massive steel drum uses simple physics to calm the violent incoming fluid stream. The mixture is held in the drum for about 5 minutes, allowing gravity to do the work. The heavy salt water settles to the very bottom, while the lighter crude oil forms a distinct layer floating right in the middle. At the same time, carefully reducing the pressure inside the vessel allows the highly volatile natural gas to bubble out of the liquid, where it is safely siphoned off through the top valves. The entire topside processing phase is essentially an exercise in controlled depressurization. It takes a deadly, chaotic geyser and successfully transforms it into a stable, market-ready commodity. Once the crude is stabilized, operators face a massive logistical problem. You have hundreds of thousands of barrels of oil, and you are hundreds of miles away from the nearest land or pipeline. This is where the hull of the FPSO unit comes into play. These vessels have an immense footprint, easily stretching the length of 3 standard football fields. That massive size translates directly to storage volume. The segregated belly tanks inside the hull can hold anywhere from 1 to 2.5 million barrels of processed crude oil. Storing the oil requires active management. The crude demands continuous temperature control. If the cargo cools down too much in the middle of the ocean, it thickens into an unpumpable, waxy sludge. Keeping this vast quantity of oil secure requires relentless monitoring. Thousands of individual sensors track the exact temperature, internal pressure, and precise volume 24 hours a day. The FPSO serves as an isolated floating vault, hoarding hundreds of millions of dollars in highly flammable inventory until an export window opens. When those holding tanks approach maximum capacity, it triggers the final phase of the offshore cycle, the arrival of a massive shuttle tanker to relieve the load. This creates an extremely dangerous physical scenario. You are bringing two colossal, heavy steel ships into very close proximity on the open, moving ocean, and you must do it without them colliding. To pull this off, the shuttle tanker relies on automated thrusters called dynamic positioning and a targeted bow loading system. These technologies work together to lock the vessel precisely into place relative to the FPSO's stern. Because a single misstep risks a catastrophic environmental spill, every aspect of this approach and connection is governed by strict, standardized industry regulations. The physical hookup happens in calculated stages. The crews shoot over messenger lines, lock in the heavy mooring hawsers to hold the ships together, and finally retrieve and connect the massive, flexible offshore loading hose directly to the tanker's bow manifold. This delicate handshake between two floating giants represents the single highest point of risk in the entire offshore life cycle. A sudden mechanical failure or a split-second loss of position here easily equates to a major disaster. Once the secure connection is confirmed, massive 5,000 horsepower cargo pumps on the FPSO activate, violently pushing the stored crude out of the hull and sending it surging through the transport hose. This gauge shows the actual speed of that transfer. During an offload, the pumps are capable of moving an astounding 8 million liters of crude oil every single hour. When the shuttle tanker is finally full, the crew carefully drains the hose to ensure not a single drop hits the ocean. The heavy hawsers are released, and the tanker sets sail for a mainland refinery. In just a matter of days, the oil moves from a highly pressurized rock tomb miles underground, up a drill pipe, through a gravity separator, into a floating vault, and finally across the open ocean. This multi-billion-dollar industrial sequence is the essential link keeping the modern world in motion.